Advanced Math Lesson 83, Simple Probability, Independent Events, and Replacement. Hopefully this isn't a difficult lesson for you, because I know I teach this lesson every single year in every single class, I think starting in pre-algebra. So hopefully this is mostly review for you guys. But nevertheless, we'll get to it. One thing I want to kind of show you real quick, which is kind of cool, because I found this in the study center a little while ago, and I'm going to keep it. It's this cool little spinny thing. I'm going to... It's got 4 colors and it's got an arrow and it spins. And the reason why I'm keeping it is exactly for this lesson probability. So for example, I've got a great probability problem right here in this little spinning thing. Also, don't tell anyone that I took it from the study center, because I don't think anyone wants it except for me, and I want it. So now it's mine. Ha! Okay. So to show an example of probability, tongue-tied. I'm just going to write because I'm tongue-tied. So probability is essentially a ratio or a division problem. It's represented like this. It's number of desired outcomes in proportion or in ratio to the number of total outcomes or possible outcomes. Don't talk to me about my spelling. So if we were to apply that ratio, that concept, that division problem to, I'm going to put the spinner there. We can see the colors so much better now. Okay, if we apply this concept to our little spinner right here, and every time I realize something that I say links to pop culture, I want to block all the comments on my channels, but none of you comment on my videos, so that makes me happy. I was just thinking, like, as soon as I was like, somebody's going to say fidget spinner, somebody's going to say it. And then, you know what? And then in like 10 years from now, while I'm still using the same videos, some student's going to be like, Mr. Claiborne, what in the world is a fidget spinner? And I'll tell him it's a ridiculous toy that didn't catch on because Mr. Claiborne was a grumpy old man. Anyways, rant complete. So, desired outcome. Let's say my desired outcome is green because my pen is green. So, I've got one green space here. So, that is one desired outcome. Now, what is my total number of outcomes? 1, 2, 3, 4. 4 total number of outcomes. That's the total number of possibilities. So, what is the probability that I will spin this spinner onto a green space? It is 1 out of 4. So that's one spin. Here's 2 spins. 3 spins. And 4 spins. I got it on the 4th try. What if I didn't? Well, sometimes it doesn't work out that way. It's a probability. Like the root word there is probable. Like probably. Anyways, so that's the quick example of probability. Let's see how this is going to show up in our problems. And then we'll compare it to independent events and replacement. Okay, so we're going to talk about dice now. I still don't have a good set of rolling dice. I know there's some floating around the school. Maybe I'll acquire some of those. Anyways, so let's talk about dice rolls. First example your book says, they tell us that 2 fair dice are rolled. So blurry. I wish the autofocus would work on this camera. It says 2 fair dice are rolled. What is the probability of getting a 7 and a number greater than 8? So in order to do this probability, we need to know how many possible outcomes there are when we roll a dice. So for the dice roll, we can use our permutations to figure this out. So for example, you would say, the first dice has 6 possibilities. The second dice has 6 possibilities. We multiply 6 by 6 in a permutation. That means there's 36 total outcomes whenever we roll a pair of dice. So we know our total number of outcomes. Our total number of outcomes is going to be out of 36. And now the question becomes, how many ways can I roll the number 7? There's 2 ways we can do this. We can either count the ways and hope we don't miss any. Like, for example, one way to get 7 is 1 and 6. And then we could also get 2 and 5. And then we could also get 3 and 4. And then we could also get 4 and 3. And then we could also get 5 and 2. And then we could also get 6 and 1. And then we got 1, 2, 3, 4, 5, 6 different outcomes. So then I can count them like that, and then 6 over 36 would give me a probability of 1/6. That's one way to do it. The other way to do it is page 500 in your textbook has a cool little chart. Page 500, cool chart. You can also look at this chart and you can see, hey, 1, 2, 3, 4, 5, 6 possibilities of getting the number 7. You could also recreate this chart. That's another way that you can do it. The chart becomes useful though. because the second part of the question is, what's the probability of getting a number greater than 8? All right. Now, if I want to get a number greater than 8, I can look at the chart and I can count this corner really quick. But I'm not going to do that. I'm going to show you the other way, because you don't really get a chart on your test. You either have to recreate the chart from memory or you have to do some logic. So if I want a number greater than 8, I have to figure out what numbers 2 dice can add up to. So 6 and 6 can add up to 12. So that's going to be the numbers 9, 10, 11, and 12. And then I have to figure out how many ways each of these can be created by a dice roll. So I'll start with 12. That's the easiest. That can be created by 6 and 6 and nothing else. So that one's only got 1. 11 has a couple of answers. It could be 5 and 6 or 6 and 5. 10. Let's see here. I could get... let's see. I can't do 1 and 9 because there's no 9-sided dice. So let's start at the highest number, 6. I could do 6 and 4. I could do 5 and 5. And then I could do 4 and 6. And then I can't do 3 and anything else. So I've got 1, 2, 3 possibilities there. Now let's go with 9. We'll start with 6 again. 6 and 3 would give me 9. 5 and 4. And then 4 and 5. And then 3 and 6. So if you notice, the logical method I'm using there is I start with the highest number dice, and then I start counting across. If I come up to, and then you'll see that some of the patterns repeat, and then some of the patterns like 5 and 5, they don't repeat because that's only 1. Okay? That's how I count them. So if I did that way, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 ways that I can get the number, a number 8 or higher. So that would become 10 over 36 possibilities. That reduces to 5 over 18, which is the correct answer. Okay, so that's how we do probability in regards to dice rolls and any other things. You just have to use a little bit of logic, and the biggest thing that gets people is the number of desired outcomes. They're going to make you have to search for how many probable desired outcomes you need. And sometimes they make you search for the total number of probable outcomes. Now let's talk about independent events. Independent events are related to coin tosses. Or rather, coin tosses are the best way to explain these. Do I have a coin? Man, that's what I get for not carrying money or cash. But the point is, I think this is a logic problem I've thrown at you before. Let's say Johnny tosses a coin 3 times, and all 3 times he gets heads. What's the probability that he'll get heads on the 4th toss? Some of you may be trying to do math on like, okay, well, if he got 3 heads before, then it's probably going to be 3 out of 4 or something like that. No, it's an independent event. Every single coin toss has a probability of 1 out of 2, right? So, because how he tosses the coin does not depend on what happened previously, okay? Now, if you wanted to show recurring events, like, for example, what's the probability of Johnny tossing a coin and getting heads 3 times? That's a dependent event, okay? So dependent events depend on each other, and that's where we get this little tree in our textbook. So the first coin toss has a 1 in 2 chance, right? The next coin toss still has a 1 in 2 chance, but we see this tree split off. Depending on what happened on the first coin toss, that changes the outcome, right? And it changes the outcome again on the second coin toss. And we see that this tower is exponentially getting larger and larger and larger. So in order for him to get heads 3 times, he's got to follow a specific path. He's got to get heads, heads, and then heads. All right, so that's 1 path. But how many paths are there? He could go heads, heads, tails. That's 2 paths. He could go heads, tails, heads. That's 3 paths. Heads, tails, tails. That's 4. He could go tails, heads, heads. That's 5. Tails, heads, tails, that's 6, or you go tails, tails, heads, that's 7, or tails, 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 that's 8. So there's 8 possible outcomes here. So the probability of him getting heads, heads, heads is actually 1 out of 8. Now, how do we do this without drawing giant charts with triangles and stuff like that? Well, we take the multiple probabilities and we turn them into a permutation, right? So it's just like here, how we found the number of rolls to get total number of dice. So we would take that probability of the coin toss, which is 1 out of 2. Because remember, I said each coin toss has a 1 out of 2 probability. It's an independent event. And let's say, here we go. Let's use a dice. Let's say I rolled a single dice, 3 times in a row. What's the probability of me rolling the number 4 all 3 times, right? So for that, I've got 3 slots for my permutation, right? Right. And then I've got 6 options, or well, my probability to roll the number 4, that's one probable outcome out of 6 possible. So it's going to be 1/6 times 1/6 times 1/6. So what I do there is I just multiply these. 6 times 6 gives me 36. 36 times 6, ooh, let's see here, 180, 36, 216. So that is going to give me a probability of 1 out of 216 to get 4 every single time. I can do the same thing. I could say, I have a single 6-sided die. I roll it 3 times in a row. What's the probability of me getting an odd number every single time? So remember, 6-sided die, that's 3 out of 6 probability for an odd number. So that's just going to become 1/2. So the probability I've got, if I roll it 3 times, is going to be the permutation of 1/2 P3. So 1/2 times 1/2 times 1/2, which is going to give me a probability of 1/8. So that's independent and dependent events, okay? Independent events are each individual dice roll, each individual coin flip. Dependent events are multiple dice rolls, multiple coin flips. Now let's talk about replacement. Replacement is the very last one. Let's do this. Okay, so let's say in my hand I have 5 markers, as I do. Whoops. Wait. Wow, that purple looks so blue. Let's replace that with red. All right, so I've got 5 markers in my hand. If I pick one up at random, what's the probability of me getting a green marker? Yes, there are 2 green markers. All right, so the probability there, if I take one marker out of my hand, I've got 2 favorable outcomes. So we'll go ahead and write that down. Out of a total possible of 5 outcomes, right? So I've got 2. Well, let's make this bigger so I don't have to refocus. I've got 2 out of 5. That didn't work out so well. It's still a little blurry. Close enough. So probability is 2 out of 5. All right, so let's say I reach in and I grab a marker, but it's not green. Okay, so now what's the probability on the second draw that I'll get a green marker? Is it still 2 out of 5? No, it is now 2 out of 4 because I have not replaced the marker that I drew, right? So that is called without replacement. Now let's say I replaced it every single time. So let's say I drew a green one, right? So I got a green one. And then on the next draw, I put it back in, right? And then I drew a red one, okay? But then on the next draw, I drew it back in. Between each draw, the probability doesn't change. But if I don't replace it, let's say I take a red one, I'm at 2 out of 4. On the next draw, I take a green one. Now my probability changes to 1 out of 3, okay? So this is called without replacement. With replacement is where every time you take one out of the pot, it goes right back in before you do the next draw. That's with replacement, that's without replacement, and that should not be too difficult to apply to your probability and permutation problems. If you guys have any questions, let me know on Moodle, and I will see you in class.